We'll talk about differentials here in this section. What I will conclude with in this section is to examine differentials using analysis, that is, trying to approximate the so-called change in z, this increment of z, using some delta and some epsilon. So we'll just work directly with the definition to see if we can find that. And so you recall from Calculus 1, you talked about differentials. What are they? Just delta x and delta y, or the so-called differentials that you looked at before. So dx and dy are approximated by delta x and delta y respectively. So that is, the delta x tries to approximate dx, and delta y tries to approximate dy. So we can talk about the so-called total differential. Here we call it dz, which makes use of partials, since the function z consists of a function of two variables. So here this becomes the partial of the function z, if you will, with respect to x, times its increment or its differential dx, plus the partial of z with respect to y times dy. Or you may write it dz is equal to this partial of f with respect to x dx plus the partial of f with respect to y times dy. And several ways you can write that. There's another notation as well that you can write it as. If they ask for the increment of z, this increment of z, it kind of acts like the change in y, but here the change in z is with respect to x and y. So the increment of z, we call it delta z, is equal to this f of x plus delta x comma y plus delta y minus f of x y. The increment wants to approximate dz. So the increment of z wants to approximate that total differential. What is the differentials used for? And I don't get into the problems of that, and I should, but I don't. But I save my time for the analysis. But what do we use differentials for? Instrument and machine measurement, instrument and machine measurement, basically becomes the driving force of the differentials. Instrument should say tool, if you will. Instrument, you may think about a oboe or a saxophone, but here, tool or machine measurement. There may be an error in the measurement. You want to be able to calculate that error. We call that the differential. Here in this case, or the increment. We say that the exact measurement would be the so-called dz, or the total differential, and the error would be the increment. Let me write it here. Exactly the error is this dz, and the exact or the calculated measurement is neat because the way they're getting that exact measurement goes all the way back to Isaac Newton and is what the computer gives. We have computers today. So what they do is they compare dz with delta z, and they look at to see if the so-called hand measurement, the error of that, how significant is that? So they give that within a plus or minus ratio, that within a certain boundary, it's okay to have certain errors in the measurement. If you're measuring by hand, ruler, if you will, something like that, you may be off just a little bit, a little centimeter or so. How much of that can we allow for the instrumentation, the measurement of whatever that's being constructed or being evaluated would be allowed? And it's the same effect whether it's medicine, what error in the dosage can be allowed. You don't want to harm anybody by giving them too much or too less. Pardon me? Yes, sir. In chemical solutions as well, you're going to have that same type of, delta, if you will. Yes, sir. Yeah. So for this, let's find the total differential. The total differential, again, remember, is the dz. The dz is the partial of z with respect to x times dx plus the partial of z with respect to y times dy. So here, dz, I take the partial with respect to x, I get 15x squared times y squared times dz, plus the partial of z with respect to y, that's 10x to the third times y times dy. That's it. Well, the good thing, you see how this section builds off the previous section. So you have those partial derivatives, you can go ahead and get these total differentials with no problem. Okay, you do this one. sir? The previous one? You sure? Okay. No, you're fine. All right. Let's see. Did you get this? dz is equal to 6x squared y minus 8y to the 4th dx plus 2x to the 3rd minus 32x y to the 3rd dy. Yep. Did you write your answer like that? That's not correct. Right. Okay. All righty. Remember that first part is the partial of z with respect to x. So you look at all of that and take the partial derivative with respect to x. And then the second part over there is the partial of z with respect to y. Okay. All right, very good. Now, here's what I did with this problem. I went ahead and measured, took this guy to be the top of a ellipsoid, just the top part of it. And I did some measuring, considering z, or trying to come up with the volume of such. What I did, I took one point and I looked at the value of f of 2 comma y. And then I looked at, if I moved a little bit from that x from 2, if I moved a little bit from that y to here 0.05, looked at the change in that. I want to calculate two things. I want to calculate ultimately delta z, the increment, then I want to calculate the so-called total differential to see how close does this increment come to the total differential. What's the total differential? I'm sorry, what's the increment, delta z? This is what's being measured by hand, and dz is what the computer is measuring, calculating using a formula, right? So you got hand measurement versus what the code says it ought to be. The error would actually be just taking the difference between the dz and the delta z, and then there's a manual that says that from the instrument measurement to the exact value, we allow this particular error within some boundary. Right? Now, here's the cool thing. The engineer who is on that field measuring and doing these calculations, he's using the manual to make sure that that whatever they're trying to construct is within the guidelines. The mathematician, the scientist, the one typically either master level or PhD, they're the ones producing the manual. So they're the ones making sure that error is actually correct. And they have to, after a certain length of time, due to temperature change and all that, they have to go back and reevaluate that because things can change over time. I see that a lot with engineers testing tires on cars and vehicles. After a certain length of time, they have to go back and measure the durability of that tire under all different types of stresses. Right? And so they say that, you know, within these boundaries of stress modules, this tire can last this long or under this particular thread count. Somebody has to calculate all of that. Yes, sir. Yes. Yes, ellipsoid. Yes, okay. And at this point, who really cares, right? Ellipsoid, it's a stupid graph, right? Oh, man. So, but thank you, sir. That's a very intelligent question. I'm sorry I gave you a lame answer, but yeah. Yeah, it's one of them, you know. Oh, man. It gets technical, and the reason why it gets technical, if you treat f as a number, just a fixed number, a scalar, then this guy becomes an ellipse. But if f is actually z, variable, then it's an ellipsoid. So. Yeah. Still, come back and graph it and actually look at it. Yeah. Yeah, you know, it's, come on, guys. I got a hamburger in my office waiting on me. You know, man, that's what I'm trying to get to after class. No. Let's just work this dang on problem right here. Very good stuff. No, you all are great, man. I love this class. So let's look at part A. And so I need to find f of 2 comma 1. So this is 16 minus 4 minus 1. So I get 16 minus 5, get 11. What about f of 2.1 comma 1.5? This is 16 minus 2.1 to be squared minus 1.05 to be squared. And when you calculate that on a calculator, I get 10.4875. Now this increment dz is f of x plus delta x comma y minus y plus delta y minus f of x y. This is 10.4875 minus 11. You see the delta x is 0.1 and the delta y is 0.05. So the f of x y is f of 2 comma 1, right? You get the 11. Then the f of x plus delta x comma y plus delta y is f of 2.1 comma 1.05. Are you with me? So that x plus delta x, that's the change in x, right? I'm going from 2 to 2.1. So then is that measurement, is that correct? So here they're measuring by hand, and so you find the difference. I get negative 0.5125. Yes. Yeah. I mean that's what's allowed, plus or minus. Here, when you just calculate that, you get negative, but in the actual error, plus or minus is fine, right? Yes, sir. So it says I need to find the total differential, dz. So this is the partial of x, f with respect to x, excuse me, times dx plus the partial of f with respect to y times dz, dy, excuse me. So the partial of f with respect to x is negative 2x, and the partial of f with respect to y is negative 2y. So this is negative 2x times dx minus 2y times dy. Okay. So we're going to use this delta x to approximate the dx, and we'll use delta y to approximate dy. So here, dx, if it's set to be this delta x, that's 0.1. And dy, being approximated by delta y, that's 0.05. X is equal to 2, y is equal to 1. Right? So then we get dz is equal to negative 2 times x, that's 2, times delta x, 0.1, minus 2 times y, that's 1, times the change in y, 0.05. Negative 0.5. So if we were actually on a site, and if you had a manual, the manual would read that the error should be within a certain plus or minus delta. Now, what would that be? That would be this, that if you take here this absolute value of dz minus the increment, so here we get the absolute value of 0.5 minus this negative 0.5125. So here we get 0.0125. You may see something like a plus or minus, in front of that. So that would be the difference. So we call this the so-called error. Now, they don't ask for that for the problem. All they want is to find here dz, and then that delta z. Z. in Calculus 1, when you had differentials, you call that the propagated error. You got the propagated error, measurement error. All right. Now, with that, let me give you one to do. Do this one. And oh, yeah, by the way, on the test, you know, you can't use a graphing calculator, but you can just use a regular scientific calculator, TI 3637, something like that. Did you get delta z for part A, the increment? What'd you get for that? No, delta z, 0.5125, right. Good. Hopefully you saw the similarities in some of the numbers with this problem and the previous problem. What'd you get for dz? 0.5, yes. So delta z, you get 0.5125, and then dz, 0.5. Everybody get that? Okay. Good. What is this graph? It's a quadric. It's a quadric surface. What is it? Because look, this f of xy is z. Paraboloid? Yep. Elliptic paraboloid. So what about that previous one? What is that? This is z equal to. It's a quadric surface. Z equal to 16 minus x squared minus y squared. It's an elliptic paraboloid too, but it's headed in the other direction because of the 16 minus x squared minus y squared. If you look at it, this is, you got z equal to 16 minus x squared minus y squared. This implies that this becomes, if I add x squared plus y squared on both sides, then I get x squared plus y squared is equal to 16 minus z. So because of that minus on the z, it flips it. Its top peak is 16. So they're both elliptic paraboloids. I thought about it while y'all were working the problem. Okay. Well, good. Two more things here. Differentiability, as we want to investigate the analysis in the mathematics. We define a function that is said to be differentiable, and here this idea of differentiability, we say that a function f, z equal to f of xy, is differentiable at some point x naught, y naught, if we can write the increment delta z in this form. We can write it as the partial of f with respect to x at some point times delta x plus the partial of f with respect to y at the point delta y plus some tilde. The tilde is some epsilon sub 1 times delta x plus some epsilon sub 2 delta y. What is epsilon 1, epsilon 2? We don't know. It has to be determined from the simplification of the increment, where both the restriction on epsilon sub 1 and epsilon sub 2 goes to 0, but that depends on as delta x go to 0 and as delta y go to 0. In other words, can we force epsilon sub 1, epsilon sub 2 to go to 0 as delta x, delta y gets close and close to the origin? When that happens, all you end up with is the increment equaling the total differential. Right? Isn't the first part, this term here plus that, without the epsilon sub 1, epsilon sub 2, isn't that the formula for the total differential? Yeah, it is. So let's see. If this happens not just at some point, but if it happens at every point in a region R, we say that the function f is differentiable in the entire region. So here's the problem, and a problem like this is also on the test. Show that the function is differentiable by finding values epsilon sub 1, epsilon sub 2 as designated in the definition of differentiability, and verify that both epsilon 1, epsilon 2 sub 2 both go to 0 as delta x, delta y shrink closer and close to the origin. So all you do is you start by writing the definition of the increment. You write that out based on the function f. Simplify it, see what you have, and then write that in the form for the definition of differentiability, and you got it. No? Let's see. That's my French that I only learned. No? Yeah. And I learned that from Pepe Le Pew. Yeah. No? Yeah, you know. Do you like me? No? You know. Anyway. So begin by writing the increment of z, delta z. So delta z, you remember, is equal to f of x plus delta x comma y plus delta y minus f of xy. I do that on this function. So this is delta z is equal to x plus, yes, delta x to be squared minus 2 times parentheses x plus delta x plus y plus delta y, now minus the function f of xy. So minus brackets x squared minus 2x plus y. I'm just going to work with this and simplify it. Now, in the simplification, two things you want to keep in mind. What is the partial of f with respect to x? Use the shortcut. We look at it. We get 2x minus 2. And what is the partial of f with respect to y? It's just 1. Keep that in mind as we simplify this increment. Okay? So this increment of z is, in simplification of this is x squared plus 2x delta x plus, yes, delta x squared minus 2x minus 2 delta x plus y plus delta y minus x squared plus 2x minus y. Let's see what cancels out. X squared cancels out. Y minus y cancels out. Minus 2x plus 2x cancels out, as they should. Here, delta z is equal to 2x delta x plus delta x to be squared minus 2 delta x plus delta y. Now, we said that the partial, you remember, the partial of f with respect to x is 2x minus 2, and the partial of f with respect to y is equal to 1. You keep that in mind because I want to write this guy basically as the total differential. So the total differential is first the partial of f with respect to x times dx. Here dx is being approximated by delta x. Then plus the partial of f with respect to y times dy or delta y. So if that be the case, the partial of f with respect to x is 2x minus 2. So here I have a 2x, I have a minus 2. So this is 2x minus 2. They're both times delta x. Right? And then now, plus I look for a delta y. 1 times delta y. There it is right there. You see that 1 right there is 1 times delta y. Right? So here, I write this as plus 1 times delta y. Now whatever I have left becomes the epsilon times the deltas. So this is plus, all I have left is a delta x squared. So this is delta x parentheses times delta x plus, I don't have a delta y for that epsilon sub 2, or do I? I do. It's a 0. It's 0 times delta y. Kind of hard to see 0. You can put 0 in there, it won't hurt anything, because 0 in modern or abstract algebra is said to be the additive identity. X plus 0 is the same thing as 0 plus x is the same thing as x, but the 0 is always there. So this guy, delta z, this is the partial of f with respect to x times delta x plus the partial of f with respect to y times delta y plus epsilon sub 1 times delta x plus epsilon sub 2 times delta y, where epsilon sub 1 is equal to delta x. That's what I have here, right? And this is epsilon sub 1, epsilon sub 2. And epsilon sub 2 is equal to 0. Right? They both go to 0 as delta x comma delta y goes to the origin. Okay, that's it. Now I have one here, but my time is limited. I have one more problem to work, so I will leave that problem for you to do later. A problem like that will be on the test. So this is online, so make sure you can do that one. Okay. Now the last thing is to be able to prove that a function of several variables is continuous. But we have a problem because there are some problems, piecewise functions, where the function may not be continuous, but somehow the partial derivatives may be differentiable. It's like a contradiction. We're using an argument from Calculus 1. The argument is this, that if a function is differentiable, then the implication is the function is continuous. Because in the definition of differentiability is continuity. Do you agree that differentiability is a stronger clause than continuity? Are you with me? Differentiability is a stronger statement because it includes continuity within it. For a function to be differentiable, it has to be continuous at some particular point. So the argument is, if differentiability implies continuity, then the contrapositive is equivalent. The contrapositive, if P implies Q, the contrapositive is also true if the argument is true. If the original argument is true, its contrapositive is true. If P implies Q is true, then if not Q implies not P is also true. Are you with me? So the statement here is, if F is differentiable at some point, then F is also continuous. At that point. This is a theorem. Its contrapositive is also true. If P implies Q is true, then the contrapositive not Q implies not P. It's also true. So here, the contrapositive is also true. That is, if F is not continuous at a point, then F is not differentiable at that point. Here, they call this theorem a sufficient condition for differentiability. That is, that if F is a function of x and y, and if the partial derivatives, the first partial derivatives are continuous in some open interval, then F is differentiable on R. We will find a problem that says that I get the partial derivatives to be continuous, but the function is not differentiable. We get something that says the complete opposite. And so we use my theorem and then this corollary that I'm giving you right here. Corollary is a consequence from a major theorem. corollary. Here's the problem. Use the function, this function f, to show that the partial derivatives at the origin, the partial of f with respect to x at the origin, the partial of f with respect to y, they exist. In other words, they're continuous. But the function is not differentiable. Here's what they're trying to say. They're trying to say that you cannot say that just because a function is continuous that it's also differentiable, because continuity does not imply differentiability. Right? Differentiability ought to imply continuity. But here, this particular problem kind of breaks that. Why? Because it's piecewise. It says that when x and y is not the origin, use this value. But when x and y is at the origin, use 0. So it has a jump. Well, you know that anytime a function has jumps in it, that it's not going to be differentiable. Right? It's not going to have a derivative. And so that's what they're trying to get at. But here, this is a function that depends on several things, x and y. So the partial derivatives are continuous, but the function is not differentiable. Okay? So let me show you that quickly. So we're going to show that the first part, we're going to show that these partial derivatives exist. We use the definition. This is the limit as delta x goes to 0. Remember, this is f of here. X is 0 plus delta x comma 0 minus f of 0 comma 0 all over delta x. This is the limit as delta x goes to 0. Here, this is f of delta x comma 0. So wherever I have an x, I write delta x. So this is 5 delta x squared times 0 all over delta x to the third plus a 0. Then this is minus 0 all over delta x. You simplify that, and notice that the numerator is 0. This is the limit of 0 over delta x as delta x goes to 0. To say as delta x goes to 0 does not mean delta x is 0. As delta x goes to 0 means as delta x goes to 0. It's going to 0. It's not already at 0. But the numerator is already at 0, so basically I'm dividing 0 by some small number. Right? I get 0. I don't get undefined, I get 0. Because 0 gets to 0 quicker than delta x as delta x goes to 0 gets to 0. Too many words. And so the partial of f with respect to y at the origin is equal to the limit is delta y. And look, folks, the problems that I'm working on in class, and the reason why I'm taking time, these are test problems. Okay. You know, why are we doing that? It's going to be on the test. So here, this is the limit as f of here, x is fixed, so y becomes the change. This is 0 plus delta y minus f of 0 comma 0 all over delta y. Same thing happens there. If the limit as delta y goes to 0, this is f of, 0 comma delta y minus f of 0 comma 0 all over delta y. It's the limit as delta y goes to 0. This is 0 over delta y, and that's 0. So we get the partial derivatives exist, that they're continuous, but that's not a strong clause to say that the function is differentiable. Let me show you. Part B. To show continuity, we look at F as it travels to the origin along different paths. It should be. It doesn't matter how you get to grandmama's house, you end up at grandmama's house. But what happens here, when you take different paths, I get different values, and that's not supposed to be. If it's supposed to be continuous, remember in calculus 1 we said that the left-sided limit must equal the right-sided limit for the limit to be exist as x goes to a. So as x goes to a from the left, as x goes to a from the right, I should get the same thing. So if I'm going from the left and to the right and I end up at this point, good. But if I'm doing this, right, then the limit does not exist. It's not continuous. If it's not continuous, what I'm using, my theorem, is not continuous. That means that it's not differentiable. So let me show you. So here I'm going to take this function and investigate the path. So you got x. Investigate the path, and I'm going to say as y is being traced along the x-axis. Here they're still going to 0, 0 of f of x, y. So this is the limit. Here this is, yes, along the line y equal to x. That's what I'm tracing this along, a different path. So this is the limit as x comma x goes to the origin. Basically what I'm saying is x equals to y. So I get 5x squared times y, or 5x cubed over x cubed plus x cubed. I get the limit as x comma x goes to the origin. This gives me 5x to the third over 2x to the third. I get 5 over 2. Now I expect to travel at another path, and I should end up with the same value, 5 over 2. If I do, then we say it's continuous. Let's see. Look at f along a different path. Say here, let's say that y is already at 0. So the limit is x comma 0 function of x, y. This is the limit x comma 0 goes to 0 comma 0. This was f of x squared y over x to the third plus y to the third. This is equal to the limit as x comma 0 goes to 0 comma 0. Here what I have is, since y is already 0, this is 0 all over x to the third. So here x is not at 0 yet, but the numerator is already 0, so I get 0. And it doesn't matter what path you can trace along y going along a parabola trying to get there. So as you can say, as y goes to x squared, you can look at that. It doesn't matter which paths you take, you're going to keep on getting different values. So to get different values means that the function is not continuous at 0 comma 0. Get different values. So if it's not continuous, again, Did I write it? I wrote it here. If f is not continuous at a point, then f is not differentiable at that point. I'm using my corollary. So notice here that f is not continuous, because I get different values. I get 5/2 here along that path. I get 0 down there along that path. F is not continuous at 0, 0. This implies, by the corollary, f is not differentiable at 0, 0. Okay. That's actually a proof. Yep. Well, good. Well, that finishes that section, so you should be able to complete now all the homework for 13.1 to 13.4. Go ahead and look at my video over the weekend on 13.5. I will cover 13.5 in class on Monday, and then we'll review for the test. Okay? Thank you. Yes, sir. I have this on the video this afternoon.